Okay, hi everybody. Welcome to the second day of the bootcamp. So the next two talks are going to be by Dinur, and she'll give us an introduction to high-dimensional expanders and tell you all about it. So take it away, Irit.
Thank you, Dol, and hi everyone. I hope you are having a great time at Simon's and at the bootcamp, and I hope to come join you. Sorry I'm not there right now, but I'm sure you're going to have a great time. So try not to ruin it. Let me start. I'm going to talk about high-dimensional expanders. So the first definition I must start with is definition of just expanders in graphs. So, expander graphs are such a fundamental object in computer science and actually in many, many areas in mathematics. And I'm not going to spend time saying how useful and important they are. Let's just say the definition that we will use here. I assume you've all seen many other definitions and relations between them. For us, a graph is going to be called a lambda spectral expander if, when I look at A sub g, I have this notation here, A sub g is supposed to be the adjacency matrix of the graph, but normalized. So you should think of it maybe as like the random walk matrix of the graph. A sub g is going to be similar in spectral norm to the adjacency matrix 1 over n times j. That's the adjacency matrix of the complete graph with self loops. And basically it says that a random walk on our graph, which is sparse typically, is going to behave, if you view it spectrally, as if you're just walking from vertex to vertex randomly, choosing the next vertex independently of what happened before. This is a kind of a good way to think about an expander, is that it really approximates, it's a sparse graph, but it approximates the complete graph up to this error term of lambda. Lambda is a bound on the second largest eigenvalue, and we actually have two variants of this definition, one-sided and two-sided. One-sided is when all the eigenvalues except for the top eigenvalue, so I have them here, are bounded by lambda. So lambda 2 is bounded by lambda. And two-sided is where all the eigenvalues from lambda n to lambda 2 are between minus lambda and lambda. So that's a stronger bound. It's two-sided. And a useful way to think of the definition of expansion is that when you take the expectation over, expectation over a random edge, and you look at fu times fv, and you compare it to the same kind of form, except now u and v are completely independent, then these two expectations are similar, and their difference is no more than lambda. Okay, and I guess I included here also the one-sided definition. This says that a minus g is bounded by lambda I in the semi-definite order. Okay, so that's the definition of an expander. It really says that the graph is very well connected, and I'm not going to give motivation, assuming that we've all seen these things. Let me move straight to defining expansion in higher dimensions. So a higher dimensional graph would typically be a hypergraph, and we're going to use the definition of a simplicial complex, which we can view as a hypergraph that is downwards closed, and it's kind of more convenient to work with. So let's see what the definition is. We're looking at a simplicial complex, which has a set of vertices x0, and then a set of edges x1, and so on, a set of d faces x sub d. And the d face is just a set of d plus 1 vertices. And the property of a simplicial complex is that if you have some face in x, S, then if T is some subset of S, T must also be in X. So in other words, you have a collection of D plus 1 sets, and every subset of them is also included in your simplicial complex. It's like a hypergraph where you close downwards. And we will soon see why we like this downwards closure property. So first, let's just look at a picture of an example simplicial complex. So here we have a graph on 6 vertices. So we have 6 vertices and maybe 7 edges. And we also have something new, which is the triangle. So we have here x0 are the vertices, x1 are the edges, this is just as usual, and x2 are just a collection of sets of 3 elements, so 1, 2, 3, 2, 3, 4, and 4, 5, 6. These are the so-called triangles or two faces, and this is a simplicial complex. And now I want to come to the first definition that's kind of new and interesting, and this is a definition of a link. So in a simplicial complex, there is this notion of a link, which is like a neighborhood of a face. So if you have a face V, you can think of V as a vertex, but more generally, it can be a face of a larger dimension. Then the link is obtained by looking at all the faces that contain this V. So all the faces above V, okay, you look at all the faces S in your complex that contain V, and then the link is comprised of these faces, but when you remove V from them. Okay, since you're in a simplicial complex setting, you know that if S is in the complex, then S minus V is actually also in the complex. So this happens to also be a face in the original complex X. Okay, let's look at an example pertaining to the complex that we have a picture here. So let's look at the link of the vertex 3. Here's the vertex 3. I need to look at all the faces that contain 3. So I have here this edge, and this edge. And for each of them, I need to remove 3 from them. So I end up with these 3 vertices. And I also need to look at all the triangles that contain 3. So I have this triangle. When I remove 3 from it, I get this edge. And from this triangle, when I remove 3, I get this edge. So all in all, this is the graph that I get. The vertices are the neighbors of the vertex 3, 1, 2, and 4. And the edges are the result of taking the triangles and removing our vertex from them. So what's the link of the vertex 4 in this example? Again, I have a vertex for every neighbor, and I have 2 triangles, so it's going to give me 2 edges, and this is exactly the link. And notice that in this case, the link of the vertex 3 is connected, but the link of the vertex 4 is actually not connected. So notice that we had a 2-dimensional complex, and now we looked at the link, and now the link itself is a 1-dimensional complex. So always the link of a vertex is going to have 1 dimension less. And if you look at the link of a higher dimensional face, then the dimensions will decrease proportionally. Okay, so now that we have defined the links, we are ready to give a definition of a high-dimensional expander. Now, I'm going to say that this definition is not possibly the first definition that comes to mind. And really, for many years, people have studied various ways to define expansion of hypergraphs, and there's many other definitions that are useful in other settings, but kind of in this area, I'm going to give today 2 definitions, this one and a random walk definition, and you'll see they're maybe not the first that come to mind, but they're still kind of powerful. Okay, so let's see what the definition is. So the definition is going to talk about what happens in the links. So we're going to say that a d-dimensional complex X is a lambda link expander if for every face in our complex whose dimension is 2 below the top dimension or even smaller. So if the complex is d-dimensional, we only look at V's whose dimension is d minus 2 or less. And then once you fix this face V, you look at the link of V, X sub V, which we just defined. And X sub V can be a higher dimensional complex. It's not necessarily a graph, but I can look at the vertices of X sub V. This is denoted XV0. So these are basically just the neighbors of V. And the edges of X sub V. These are basically the pairs of neighbors of V that participate in a triangle with V. Okay, so this gives me a graph. This is called the one skeleton of the link. So again, I look at a face V, I look at this neighborhood of V and the kind of the one skeleton of what's around V. And I require that this graph itself is a lambda expander. Okay, this is the definition. And in this case, sometimes people call this lambda spectral high-dimensional expander or link expander. These are the names so far. Let me say that this definition came up, or kind of was developed in parallel with the development of this theory. And I think mainly it was developed in a sequence of works by Kaufman and Lubotsky and Kashdan and Shai Evra, where they actually looked at a very specific simplicial complex called the LSV complex, which I'll talk about soon. And they were trying to understand that complex. And the definition of this complex is very difficult because it's defined by quotients of something. And the way they managed to get a handle on that complex is by looking at the links and understanding the links. And then they managed to prove really wonderful properties about this complex. And that's how this definition kind of arose, because it was enough to require that the links satisfy these properties. And I forgot to say the complex needs to be connected. And just being connected and having the links being good spectral expanders is already enough for a lot. And we'll see that now. So that's the origin of this definition. In order to appreciate this definition, I think the best thing for us to do is to look at a few examples of high-dimensional expanders and see how they behave with respect to this definition. Okay, so in graphs, the model expander, well, people will tell you that a random graph is the model expander, but let me say that the model expander is actually the complete graph. The reason we like it less is because it's dense. On the other hand, being dense, it's really the most connected graph. So similarly, we have the complex. You have a graph of n faces, and then any dimension possible I faces. So you take all possible 2 edges, all possible n choose 3 triangles to level D. And if you want, you can think of it as the scheme, where think of the scheme as also big, and it's the same as saying size, p times n. So complex. And easy to, when you think about it, to see that links complex are just the complete complex, one element less and one dimension less. Okay, here's another non-example, a random complex. So for graphs, we know that our regular graph is actually a fantastic expander, and there are still many open questions trying to construct explicitly graphs that have some properties of random graphs. In this theory, the situation is different, and we don't actually have a random model for a sparse high-dimensional expander, not even for dimension 2. So once you go above graphs, already the random theory kind of doesn't have enough power. And let's look at 2 examples. If you choose edges, each one with probability p, then if you take p small enough to consider this to be sparse, you'll not get any triangles. You can also try to say, no, I'm going to choose triangles at random and just put them in my graph. You can do that, but then if you look at a vertex and you look at its link, so this vertex participates in some number of triangles, but each of these triangles will kind of be disconnected. And it will only be connected if you choose many, many triangles. So there is some threshold. If you raise p to be large enough, this will actually be a good expander, but definitely not if you want constant degree. So random graphs are not going to be very helpful for this theory, random complexes. Here's another example that's maybe not so interesting, but it's a good warm-up for the one after. And this is the D+1 partite complex, D+1 partite complete complex. Here, what we have is a collection of subsets of vertices, each of size n, and disjoint. And then the faces are going to be D+1 tuples, where you choose one vertex from each set, from each color. Okay, so you have your D+1 colors, and you choose one vertex from each color. And I only need to tell you what the top faces are, because then you do downwards closure. So you take all subsets of these faces, and you get a simplicial complex. So let's notice that each face corresponds to a d+1 tuple. I wrote it here, V0 up to Vd in n to the d+1. So it's another way to represent tuples of elements in n, okay? And let's think, what does a link look like? So if I choose some vertex V in some, color class Vj, color class.
Hey, Irit, we cannot hear you.
Can you hear me now?
You hear me now?
Oh, wonderful.
Yes, many times.
How about now? How is it now?
How is it now?
Still.
Ah,
Irit, can you mute the iPad audio?
ah. I'm thinking about it. Okay, I had to disconnect the audio, and I think I did it now. Sorry about that.
And now it's good.
Okay, so how far back should I go?
You started explaining the complete D+1 partite complex.
Ah, the host stopped the video. Okay, that's fine. Complete bipartite complex. Thank you. Inaroko wrote something. The links. Okay, all right. So suppose I have a vertex in some color class J. Okay. All right. I have a vertex in some color class J, and I look at the link. So I need to basically look at all the faces containing this vertex. Who are they? Well, basically, I need to choose a vertex from every other color class. So I have one fewer colors, and I have still n vertices in each one. So I get a complete D-partite complex on the same, on all the remaining color classes. Basically, you can see that the skeleton of this graph is like a bunch of colors, and between each pair there's a complete bipartite graph. So this is a very good expander. So we would definitely call this a high dimensional expander. Okay. Now moving on to something that's a bit more interesting. This is the spherical building. Okay, I hope we're together still. Okay, that's good. All right. So the spherical building, maybe it will look a bit strange, but we really like it because A, it's easy to describe, And B, it is a component in these Ramanujan complexes that I told you about before. So somehow it's an important high-dimensional expander. Let's see what it is. So you fix some finite field FQ of your choice, and you fix some parameter D, it's the dimension, and then your vertices are going to be all linear subspaces of the vector space F to the D plus 2. Okay, now I'm not specifying a dimension. So we're going to take all linear subspaces of all possible dimensions. And actually the vertices come with colors. So a vertex of color I, or type I if you want, is a linear subspace of dimension I. And we let I range from 1 to D plus 1. These are all the non-trivial subspaces of F to the D plus 2. Okay, and all of these are just considered vertices. They're not higher dimensional faces. All the different linear subspaces. And now what are the faces? The faces are chains of subspaces. Okay, flags sometimes we call them. The chains are all possible tuples U1, U2 up to UD plus 1, such that UI is a linear space of dimension I, and U1 is contained in U2, is contained in U3, and so forth. So it's a chain of subspaces. That's a D face. So let's look at an example for D equals 1. I have F to the 3, and I have all possible linear spaces there. So basically, I have lines and planes. So my vertices have two types, either lines or planes. And the edges are just pairs U1, U2, where U1 is a line that is contained in U2 that is a plane. Okay, so it's a bipartite graph. It's just a one-dimensional complex. And it's you can think of it as the lines versus planes incidence graph. Sometimes, but people really like to call it the points versus lines graph in projective plane. These are the same. Okay. And notice that you can calculate exactly the degrees here. It's Q plus 1 regular. And so it's not a sparse graph, but it's a very good expander, actually. Okay. Now let's look at the example for D equals 2. Here I have F to the 4, and I have 3 types of vertices: lines, planes, and 3 spaces. And my faces are triples, U1 contained in U2, contained in U3. Now, already now notice that I don't have the same number of lines as I do the number of planes. There's many more planes in F to the 4. Okay, so the complex is not going to be regular anymore, right? The degree of a vertex U1 is going to be going here is going to be much larger than the degree going down. Okay, that's okay. So let's look at the links of this complex. Okay, first let's fix some element U2, some plane, and let's look at the link of this guy. So the vertices are all the U1s that are contained in this U2, and all the U3s that contain this plane. Okay, and the nice thing about this link is that every line that is contained in U2 is also contained in every U3 that contains U2. So you get here a complete bipartite graph. Okay, so that's obviously a very good expander. If you're asking yourself, are the links good expanders? This link is very good. What about if we take a vertex U1? So not all the links in this complex are the same, it turns out. If I start from a vertex U1 and I look at its link, I don't know why this keeps happening, then I get all the planes that contain this line and also all the 3 spaces that contain this line. And the graph between them is again the plane 3-space incidence graph, but since they all contain a line, you can kind of take a quotient and you get a graph that's isomorphic to the graph from D equals 1. It's really just, again, the lines versus planes incidence graph. And as I said before, this is actually a very good expander. So all the links in this 2-dimensional complex are very good expanders. And you can go on and see that for dimension D, you can recursively see that the links are always kind of combinations of complete partite graphs with the lower dimensional spherical buildings. So this is a very good expander. Final example is the LSV, Lubotsky, Samuels, and Vishner Ramanujan complexes. I'm not going to describe the complexes. It's beyond my ability. But let me just tell you abstractly what I know about them. So for every integer d, and for every prime power q, you have a family, an infinite family of d-dimensional complexes, such that the number of vertices in these complexes goes to infinity. But in each one of these complexes, for every vertex, the link of this vertex is just the d-1 dimensional spherical. Wow. Okay, can you hear me multiple times or once?
Multiple.
Okay, sorry about that. Okay, so I just said that we have this infinite family of complexes where the links are exactly the spherical buildings. In particular, spherical building only depends on Q and D, so it's fixed size, and the number of vertices goes to infinity. So you have here a family of connected complexes, dimension D and constant degree, and yet all the links are very good expanders because the links are themselves these spherical buildings. It's not hard to see that they're very good expanders. So really kind of the way this theory started is by looking at these objects and realizing that you can prove a lot of interesting things about them just by understanding the links, and you don't need to understand like the complete picture. And this is really the power of these objects, that they have this local to global feature. A lot of times in complexity, we want to understand some, NP-hard problem, some CSP or some global object and we don't know how to get a handle on the entire thing. So it's sometimes good to look at small pieces, and the links are nice little pieces that kind of give information. And here is a theorem that is kind of a first manifestation of this phenomena, this local to global phenomenon that says if you know something about the links, you can deduce something globally about the entire complex. And this is the trickling down theorem of Oppenheim. What does it say? It says the following: if you have a complex X, and let me start by just looking at a two-dimensional complex, but really this goes to D dimensions. So you have a two-dimensional complex, and about the graph underlying the complex, you don't know that it's an expander or anything. All you know is that it's connected. But you do know that for every vertex, the link of this vertex is actually a good lambda link expander. Okay, so you know that the graph is connected, and you know that the links are good expanders. The conclusion is that the entire graph is a good expander, and how good? It's lambda divided by 1 minus lambda. So if lambda is very small, goes to 0, then mu is almost as small as lambda, very small as well. If lambda is half or above, you don't get anything here. Okay. And just by iteratively applying this, you can get the same theorem for not a two-dimensional complex, but for a d-dimensional complex, just by first applying it from the d-2 links to the d-3 links, and then to the d-4 links, and kind of trickling down this theorem until you deduce that the entire graph is an expander. Okay, but I think it's already impressive enough to see this theorem for dimension d equals 2. So suppose you have a graph that has a bunch of triangles, and every vertex touches maybe even a constant number of edges, but you know that around every vertex, if you look at the subgraph induced by the subgraph of the link, you know that it's a lambda expander. Now, sometimes people ask, what do you mean a good expander? If every vertex sees a constant number of vertices, neighbors, how is it defined to be a good or not a good expander? Well, it is defined, right? We said that a graph is an expander if the normalized second largest eigenvalue is bounded by lambda. This is defined for a graph even on 20 vertices. You don't have to have a growing family. So that's what we mean by lambda expander. And let's see why this theorem is true, or let's see a proof of this theorem. Okay, so let's start. We have an adjacency operator, A, associated with the global graph. Okay, and let's take some eigenfunction of this A. Okay, and suppose it has eigenvalue gamma. Okay, since we already assumed that X is connected, we know that this gamma is strictly smaller than 1, but it could be like 1 minus 1 over n. And our goal is to prove that gamma is actually much smaller. Okay, so let's take this eigenfunction. We know that it's orthogonal to the all ones. By the way, I'm going to assume that my graph is regular and my complexes are regular because it makes things easy. But if you've seen these things before, you can see that when I write expectation, there is an appropriate choice of probability distribution that you don't need this assumption. If you choose the distribution correctly, then this works also for irregular complexes. Okay, so we have our eigenfunction f, and we start writing this quadratic form. Gamma equals the inner product of f with af, okay, which is just the expectation over all possible edges of f of u times f of w, okay, for all edges in the graph. Now, this is a key step. The expectation over a random edge in a graph, in this graph, can be decomposed into like a convex combination of small expectations as follows. When you choose a random edge uw, it's the same as if you first choose a random vertex v, and then you look at the link of v and you choose a random edge in the link of v. Why is this the same? Because really what's going on is that you can think of it, you're choosing a random triangle in the complex, UVW, and then you choose which pair to put as the edge and which vertex to put as the V. So you choose V randomly out of the 3 possibilities, and then the other 2 are the random edge. So you basically chose a random triangle and then a random edge in it. This is the same as just choosing a random edge. That's exactly how we define these distributions. In the case where the graph is completely regular, you just get uniform. And if the graph is not completely regular, this is exactly how you define the distribution to make the theorem work. This theorem and many other theorems. And so we get this equality that the expectation over a random edge is the same as first choosing a random vertex and then taking expectation only over the edges inside the link. Okay, now once we have this equality, we can use stuff that we know about the links. So we have gamma equal to this expectation over V, and then expectation of something that's going on inside the link of V, this. And so we can even, to emphasize, we can define f superscript V to be a function that's only defined on the vertices that are neighbors of V, and it's just the same as f. Fv of u is f of u. And we can denote A superscript V to be the adjacency operator on the link. And this is the promise that we had. What are we trying to prove? We are given a complex. We know that for every link, A sub V is a very good expander. And we want to prove that the entire operator A is a good expander. Okay, so we're now going to be able to use the fact that A sub V is a very good expander. We just write this inner expectation as the inner product of FV with AV of F of V. And then we just want to use the spectral bound, but it's best to shift F of V. F of V does not have expectation 0, so we shift it to G of V. What is G of V? It's F of V minus the expectation of F of V. Okay, G of V is a function that has expectation 0 inside the link. And by the way, what is the expectation of F of V? You look at the vertex V, you look at all of its neighbors, all the U's that neighbor it, and you take the expectation there. This is exactly what the operator A does. When you apply A on F and look at point V, you just take the expectation over the neighbors of V, of F of V. So you get AF of V. But F was assumed to be an eigenfunction with eigenvalue gamma. So AF at point V equals gamma F at point V. So that's why we have here that the expectation of F is equal to gamma times F of V. Okay, so now we can use the fact that AV itself is a good expander to get this upper bound that on one hand you have here the expectation of F of V, which we already know now is gamma of F of V, but squared. This is like remember when we said that an expander is when AV is like the J, like the complete graph operator. So this is the term you get from J. And then this is the error term. This bound is lambda times the norm of GV squared. And now all we have to do is take these values, take expectation over V and see what we got. So I guess I have here G of V. Okay, G of V squared, this is Pythagoras theorem, GV squared plus this constant thing. This is like the constant function, which is orthogonal to GV. The sum of these squares equals this square. So you get this equation, you take expectation over V, and what you get is, well, this is just the expectation of F squared, which we assumed is 1. And this is again the expectation of F squared, which we assumed is 1. So you get 1 minus gamma squared. Okay, so all in all, we got that gamma on this side is less than 1 minus gamma squared. Okay, so sorry, times lambda. I forgot the lambda. Okay, so here I need to add a lambda. Okay, so okay, anyway, this is what we get. Gamma is less than gamma squared plus lambda times 1 minus gamma squared. And when you rearrange it, you get the required result. So one way to understand this proof is that I think the key step is that we managed to break the expectation over a typical edge here in the center to a bunch of local expectations, and then we managed to use the knowledge that we had about the links. And that's how kind of the expansion in the links was strong enough to force global expansion. I think it's quite remarkable. Okay. Now I want to move on to talk about random walks on simplicial complexes and the up and down operators. Maybe if there's any questions before I continue. Okay. Cool. Okay, so when we think about random walks in graphs, we think of going from a vertex to a neighbor, and so on. when we have a higher dimensional complex, like we do here, we can walk on the vertices like we did before, but we can also walk on the edges. For example, we can walk from edge to vertex to another edge, and so on. We can also walk from edge to triangle to another edge, and so on. And these walks are not the same, right? If I take the walk from edge to triangle to edge, then if I start from this edge and I go to this triangle, and then I go to this edge, then I go to this triangle, then I go to this edge, I'll kind of get stuck in this component. I'll never be able to move from this edge to this edge, right? So the random walk, when I go from edge to triangle to edge in this specific complex, has two different components, whereas the random walk that goes from edge to vertex to edge to vertex to edge to vertex to edge actually manages to transverse between all of the edges in this graph. So these two random walks on the edges, one going to triangles and back down, one going to vertices and back up, have different behavior. And actually the reason for this is the link of this vertex, which is a disconnected link. He's kind of to blame for the fact that the lower walk and the upper walk don't have the same connectivity. I'm not going to go into the details too much, but you can show that if all the links are connected in all the dimensions, then the upper walk and the lower walk will have the same connectivity. Okay. So one way to think about the random walks is to draw out the simplicial complex in layer form. So you put like a blob of vertices for the vertices. So you'll have one dot for every vertex. And then you'll put another blob of vertices or points, let me say points, one for every edge. And then another blob, one for every two face, and so on. You can have more and more layers. And you can think of connecting between, say, a triangle and an edge, just if the triangle contains this edge. Okay, so then the random walk that goes from edge to triangle to edge is like a random walk in this bipartite graph, where you go like this. Okay, and so you can already see that the connectivity of going from edge to triangle to edge is the same as the connectivity of going from triangle to edge to triangle. So these two have the same connectivity and also the same expansion. If you think of like the rate of convergence of this random walk, they will have related expansion. Whereas the random walk that goes from edge to vertex to edge to vertex to edge this way is not exactly the same as the random walk that goes from edge to triangle to edge to triangle this way. These, at least superficially, they look different. And our definition of when is a complex a good random walk expander will actually compare these two random walks. Okay, so let's set up some notation. We define Ci, the set of cochains at level I, just to be all the functions from the I faces to real valued numbers. There's a whole other theory that deals with the kind of linear algebra on high dimensional expanders. It's not a whole other theory, it's a whole other part of this theory. And then you just replace the coefficients R by, say, F2, for example. And I'll say a couple of things about that later on. But for now, let Ci just be all the real valued functions on Xi. And we define an inner product between two functions to be the natural thing. You have some distribution over the faces in Xi, and you take expectation of F at point S times F prime at point S. Okay, and we also add, for convenience, we also add this extra -1 dimension layer, which just has the empty set. Okay, now we come to the definition of the up and down operators. So it's a very natural definition. The up operator takes me from I chains, so functions on the I faces, to functions on the I+1 faces. So moves me 1 dimension up. And how is it defined? It's actually defined by looking down. So if I have an I chain F, an I chain is a function on the I faces, and I want to evaluate it at a point S, what I do is I look at all the subfaces of S, T, and this notation T less than S just means the T is contained in S and it has one dimension below. Okay, so for example, if S is a triangle, then T is all the three edges inside S. Okay, so the up operator at a point S averages f of T on all the faces just one below. So in particular, if I want to define, I have a function on the edges and I want to define the up of this function to be a function on the triangles, then for every triangle, I just average the value on the three edges, and this will be my new function. U of f defined on all the triangles. And similarly, the down operator, it takes me from an I chain to an I-1 chain. Now I do the reverse operation. If I want to know what df evaluates to at a point S, I need to look at all the faces T that are just one above S. So if I want to know what df is at some vertex 4, and my function f was on the edges, then I just average the 4 values given here. And notice that the way I wrote it, I wrote expectation, and I'm kind of hiding the distribution. So there is a proper way to define distribution over the I faces, and it's always going to be with respect to that distribution. And if you're a beginner to this area, then the best thing is to think that the complex is super regular, so that every edge is contained in exactly the same number of triangles, and every triangle is contained in exactly the same number of three faces, and so on and so on. So then all these distributions are uniform. Okay, and it's kind of almost obvious to see from the picture that up and down operators are actually transposed of one another, adjoined to one another. If you have a function, a cochain in Ci and another one in Ci plus 1, then the inner product of F with dg is equal to the inner product of UF with G. So basically you can move D to this side and make it into a U. Okay, and the reason is that what does this equal, this whole thing? It really equals to the expectation over choose a face S and then choose all possible ways to choose T just above it and average F of S times G of T. Okay, alternatively, you can first choose T randomly and then choose S to be some face just below it and write G of T times F of S. And that will be, the first will be this equality, this quantity, and the second will be this quantity. So these two are really adjoint. Okay, so now when you have this object, this combinatorial object, and you want to understand various combinatorial properties of it, expansion of sets or whatnot, it's very convenient, as we know, to have a good basis, like a Fourier kind of basis, a good basis that respects or works well with these natural up and down operators. And Max will talk about this in more details later on. We will first study the high order random walks now that we defined the up and down operators. So we talked before about the lower random walk, going from I faces, from I chains to I chains by going first down and then going up. So say you have a function, you start at an edge, you go to a random vertex, and then you go to another edge. Okay, that's going first down and then back up. So we view this as the lower random walk. And the other operator is the one that starts from an I chain, first goes up to a triangle, and then back down, back to an edge. This is called the upper random walk. So let's look what these two random walks look like in the case of I equals 0, when we have functions on the vertices. This is the most familiar case when we look at graphs. We have a function on the vertices of the graph, and let's look at what do these two random walks behave like. So first, let's do the down up operator. You first apply down on your function and then you apply up. Okay, and I only write always the index I tells you on what dimension of cochains you're operating. So UI operates on CI. DI plus 1 operates on CI plus 1. Okay, so UD0 operates on C0, so it's on functions on the vertices. So basically, I start at a vertex, and now I'm supposed to go down. Well, if I'm at a vertex, how can I go down? I can go down to the empty set. Okay, so if I scroll up here, you can see it in this picture. We added this empty set layer that allows us to go down even from vertices, and every vertex, when you go down from it, you just go to the empty set. So when you go down and then back up, you're basically going to any other random vertex. Right, so going back here. So really, this operator, it starts from some vertex V, and it goes down to the empty set and then back up to any other vertex with uniform probability. This is exactly what the the all ones matrix does. I guess maybe I should have written 1 over n, so the normalized J. Okay, so that's the down up operator. What about the up down operator? The up down operator, okay, I'm starting from a vertex. I go up to one of the edges containing it. And okay, so suppose I go up to this edge. And now I go down. So I can go down either to 4 or to 3. So with probability half, I actually go back to where I started. That's this part. And with probability half, I go to a random neighbor. Do you see that? Because no matter which edge I chose, there's always going to be probability half of going back to where I started. So that's this component. And there's going to be probability half to go to some random neighbor. Okay, so the up-down, the upper random walk is not really the random walk we were hoping to get. It's a lazy version. It's lazy with probability half, it stays in place. Probability half, it goes to where we wanted. So if M is really the random walk on the graph, then the up-down is a lazy version of M. And when we defined what an expander is, and we said an expander is a graph where the adjacency matrix of this graph is a good approximation of the complete graph, we wanted to really compare these two. And we don't need this extra laziness. So we introduced this notation MI plus. This is the non-lazy upper random walk. And it's defined to be the up-down operator when we remove the laziness from it. Okay, so really the way to understand which constants to choose here, you want to have this equation satisfied. Let's look at this equation. I want to express the up-down walk as some component of laziness. This is the 1 over I plus 2 times I, plus another component, which is the non-lazy part. Okay, so when I kind of rearrange it, I get this formula. Okay, let's check it for I equals 0. For I equals 0, I get here half and here half. And M0 plus, the non-lazy upper walk, is exactly the walk that goes from a vertex. What did I do? From a vertex to a random edge containing it, and then to a random vertex in this edge, except you're not allowed to go back. So you must go here. So it's really just a random walk on the graph. Okay, so MI plus, in the case of I equals 0, is really the adjacency matrix of the graph. And so I could have defined for a graph, not for high-dimensional complex. For a graph, I could have said a graph is a lambda expander if this holds. The down-up walk, which for case of graphs is just this normalized J matrix. The difference between MI plus and the down-up walk is at most lambda or gamma here. So again, for a graph, MI plus is just the adjacency matrix. This guy is just J. Maybe I'll actually add this. So this is just J. This is, sorry, no. This is just M. This is just J. Okay, in a graph. So now we give this definition, which is really just now that you describe it this way, you see that this definition is just a generalization to higher dimensions of the definition for graphs. Really what you want is now to say, okay, I'm going to call my complex high dimensional expander with respect to random walk, so random walk expander, if you will. If for every level I, the difference between the down-up walk, the lower walk, and the upper walk is small, well, that's not quite precise because the lower walk doesn't have noticeable laziness, but the upper walk is kind of forced to have this laziness, right? If you walk from an edge to a triangle back to an edge, there's probability 1/3 that you'll go back to where you started. So you're always going to experience this laziness. So we're going to remove the laziness component. This is why we add the plus in the notation. No, it's not why we need the plus. The plus is for upper. But anyway, this is the notation for the non-lazy. And once you look at this m plus rather than the down up, I could have written here du minus ud. That would cost me this extra laziness. So instead, I remove the laziness and use the non-lazy random walk, and we define a random walk expander to have this difference being very small. Okay, and we have a one-sided version where the norm is bound in absolute value by gamma, and we have a two-sided, sorry, that's a two-sided, and the one-sided version is where you say that these are in semi-definite order, in PSD order, dominated by gamma times the identity. Okay, so this is a definition, and we have a theorem that says that the link expander definition implies the random walk definition, and also to some extent vice versa, although you do lose parameters. Vice versa says that if you satisfy the random walk definition, you have a good comparison between the upper and lower random walks, then you must also satisfy the link definition. Okay, so qualitatively, these two definitions are, I'm about to finish. Qualitatively, these two definitions are the same. And okay, after the break, we will talk more about this. Actually, maybe, do you want me to, okay, allow some questions before we take a break?
Any questions?
So is this the definition of the this definition of lambda random walk expander, does it imply like a fast mixing for the up-down walk or down-up walk?
Does it imply what for the up-down walk?
Like a fast mixing for the up-down or down-up walk.
Oh, yeah, definitely. Thanks for the question. Yes, actually, what it implies is that the spectral profile of the up-down walk is very similar up to errors that are comparable to gamma to the behavior of random walks on the complete complex. So in some sense, this allows us to say that if you're a gamma expander, and gamma is, you can think of it as very small, then random walks mix. More than that, they mix at a pace which is just like the best pace you can hope for, which is in the complete complex. Okay, so you know, for graphs, we said when is a graph an expander if it's a good approximation to the complete graph. It would be natural, maybe more natural a priori, to say, okay, we're going to define the same thing for higher dimensions. We're going to say a complex is a good expander if it's a good approximation to the complete, say, two-dimensional complex if we're in 2 dimensions. But how can we even define it? If a complex has much fewer edges than n choose 2, how can you even compare an operator that works on space of edges, that here you have few edges and here you have many edges? there's no good way to write this comparison. And this is a way to circumvent it. You say, no, I'm going to compare for the complex, the upper and the lower random walks of that complex. And I know that for the complete complex, I have very good comparison. Actually, maybe we should have checked it. For the complete complex, these two random walks, once you remove the laziness, they're identical. Okay, so you get 0 in your gamma is really 0. For our complex, okay, it's not 0, it's some gamma. But somehow this allows you to show that the random walks mix just almost as fast as in the complete complex. Thanks for the question.
Thank you.
Any more quick questions before we take a break? Okay, cool. So we'll take a break of 30 minutes and come back. So thank you, Ray.